All right, so we're going to wrap up the Roman Empire real quickly. We're going to talk about Diaphantus. Diaphantus is actually, as I said before, not a Roman. He is a Greek. And he was a Greek person in the later declining part of the museum and what you would consider Romans rising and conquering. And there are still a few scholars who are left at the museum and who are probably persecuted and will probably end up leaving. But for now, this guy, Greek, it's said that his times are around 150 to 350 AD. Now, clearly, he didn't live for 200 years. So most people say it's about 250 AD, kind of split that difference down the middle. But the thing is that we know records at this time are a little bit sketchy and can be difficult to nail down stuff. So we're not exactly sure of his dates, unfortunately. But we're going to say sometime in that time period. Okay, we know it's AD. We know it's toward the end of the Roman Empire's height. And for sure, Alexandria is starting to really go down. The museum's starting to die off and that kind of thing. So, okay, what did he do? He wrote the book called the Arithmetica. The Arithmetica, which actually was 13 books. They like to write big time. And only 6 have survived for various reasons. He wrote a book called On Polygonal Numbers. I've heard it said polygonal also, but this thing on polygonal numbers, now look at that. Those are like triangular numbers and square numbers and pentagonal numbers and things that we've already talked about. So we know that the Pythagoreans were already doing this a couple of hundred years ago, but he wrote a book on it. Unfortunately, there's only fragments that remain. So that one's mostly gone. And then he wrote something called The Prisms. Okay, which is supposed to be related to geometric shapes and things like that, those kinds of prisms. And what we know from that is that we know he wrote it because we have corollaries from his writings. And mostly those are things that other people have referenced. So the book, I don't believe there are any copies of the book left over. This is just people referencing him and his work, so we know that he was there. A lot of his works, this Arithmetica stuff here, it actually ended up translated into Arabic. Okay, so Arithmetica is actually supposed to be an Arabic name, an Arabic word. But we know that we have this word, arithmetic, in the English language, right? So it's one of those things that we have borrowed from the Arabs or taken from the Arabs. So, yeah, along with their number system. Thank you very much. We love the Arabic numbers. Okay, so he's got those things going on, but inside of the Arithmetica in particular, he worked on a bunch of number theory type stuff. And we're going to work on some of his problems today and get that finished out. That's why I didn't figure I could finish this in 10 minutes. But he worked on number theory stuff, so much so that he has earned the title Father of Algebra. Okay, because he worked on a lot of stuff. He actually pushed for, he's the first one that we know to abbreviate things in his writings. For instance, if a problem we're talking about bales of hay, he might have used H. Oh my goodness. If a problem we're talking about time, he might have used T, abbreviating things. Oh my goodness. He's the first one that we have absolute proof, I believe, of utilization of what would soon become known as variables. Okay, and so those students who get mad because you've got variables in with your numbers, I was fine, I've heard this before, I was fine in math as long as it was just adding, subtracting, and multiplying and dividing, but once you throw those variables in there, I get lost. So we can probably blame Diaphantus for that, is my thought on that. So a few things about him. Fun facts. He only worked with positive rational numbers. So, okay, you Pythagoreans, you're worried about irrational numbers. I don't care. I'm not going to worry about them. I'm going to scoot this up. Some of you might be worried about negative numbers. I'm not worried about those. I'm not going to work on them. So he didn't worry about those. If he was dealing with, say, a quadratic function or something that might have multiple solutions, he didn't care. One solution is okay by him. Okay, so for instance, for today's modern math, we might say plus or minus the square root of 9, and we might get plus or minus 3. He didn't care. He's just working on the 3. Okay, so and in a lot of situations, whenever we're doing word problems and stuff like that, even in modern math, we'll see that we only deal with the positive, right? We don't concern ourselves with the negative solution. So he was kind of a forerunner for that, maybe. Just don't worry about that negative solution. We don't care about it. Okay. He was an interesting guy because unlike the other Greeks that we've worried about so far, he was not going to do proofs. I'm just not going to do it. I'm going to content myself with working with problems that I think I can work on and actually get a solution or some kind of something coming out of it. So he was the one who defined variables and equations that looked like this. So he might have something that looked like 17 equals 119x plus 229y. Now, he might have written it out in a whole bunch of words, so it might not be quite as nice and lovely as our modern day mathematics. And what we would do today is say find x and y, right? So he might not have done that, but he was working on on problems that looked like that, problem types like that. And again, once he found one solution to this guy, he's done, even though we know could be more than one solution, right? So he's like, nope, I'm not worrying about it. I'm just dealing with one solution and I'm done. All right, so it could look different ways, but we don't care about that, okay? One of the things that it seems very likely is that he was trying to help with the notation. He knew that the notation was bad and that we're not making advances like we should be in algebraic type concepts or in calculation type concepts. And there's a problem with that, and the problem is in the notation. So he was trying to, by looking at equations and variables and stuff like that, he's trying to help with the notation as much as possible. Okay? So we know that the word arithmetic passed through the translation into the European mathematics and ended up in Renaissance math and in today's mathematics. The cool thing about him is that he was able to discover new math even while looking at what we would consider book problems. Okay, so just some stuff that we might make a kid do when they're learning their math or something like that. Just basic word problems or book problems, but he was able to learn new stuff. So he came up with, for instance, exponents up to the 6th power. Okay, cubics and stuff like that, and he realized that there was stuff that he could be working on like that. So interesting work going on. In particular, there's something that we call a Diophantine equation. So the things that really interested him, Diaphantus looked at, Pontus examined, stuff like this: z squared equals x squared plus y squared, where everything there has a power of 2, they're all squared, and he's looking at integer solutions. Okay, so he doesn't care if there's some weird fractional answer or something like that. I'm looking at integer solutions. And these things should look familiar, right? X squared plus y squared equals r squared. This is really kind of, if you really look at it, a squared plus b squared equals c squared, right? Just in a slightly different format with these really nice variable notations instead of here, a, b, and c normally represent a quantity in my right triangle, right? So he's looking at these things. It's also can look like the equation of a circle, right? X squared plus y squared equals r squared. So things that we see, we use it nowadays, modern mathematics. It's believed that this could have spurred on Fermat's last theorem. So we may not get to Fermat later in our time. He doesn't come along for quite a while, like thousands of years. But Fermat's last theorem, basically, Fermat was a famous mathematician, I think 1600s, 1500s, something like that. And many years later, what he said was he was reading a book, and he wrote in the margin, z to the n equals x to the n plus y to the n when n is greater than 2. Fermat said, I have a proof. He wrote this in the margin of a book. I have a proof, but there's too little space in the margin of this book. I have a proof for this to show that this guy, that I can get some integer solutions for this. Integer solutions whenever n is greater than 2. And I have a proof for it, but I just don't have enough space in this little bitty margin, and goodness knows I couldn't possibly pull out another sheet of paper and write it down there. So it's actually interesting because Fermat died, and this is called his last theorem because it was never proven. So for a while, Fermat's last theorem was called one of the, oh goodness, I can't remember what it's called. It's like $1 million problem. So there was a prize out there, prize money available if you could prove this, okay? Because according to Fermat, he has a proof, he just hasn't proven it yet. So interestingly enough, I was alive whenever this happened. Some of you may not have been, but I was. Andrew Wiles, oops, cannot write tonight. Andrew Wiles, in 1994, worked this famous problem out. And Fermat did not lie because there was too little space in that little bitty margin. His proof was 100+ pages, and it used calculations from a computer. So it's doubtful that Fermat actually had a proof. He probably just had a really good idea for how it would work. Or maybe he was just trying to spur people on so that they could work these problems. But in fact, I remember whenever this came out that if I remember correctly, Andrew Wiles, I think he's an English guy, they had come up with their proof and sent it in so that they could get the prize money. And there were actually errors in the proof. Can you imagine proofreading a 100+ page proof? So there were errors in the proof page, the pages of the proof, so they had to go back and fix their errors, but they did in fact prove it, and I'm pretty sure they got that prize money, so that's pretty impressive. Okay, so let's talk about Diaphantus because, okay, we need things like this that have integer solutions. Okay, got it. What does that mean? Okay. So for our purposes, we're going to work two problems right now. One is out of your book. Find three numbers so that any two of them added together, and I'm paraphrasing, but you'll understand, give the sums 43, 51, and 34. Okay. So these are supposed to be equations that have integer solutions. If we were doing this in modern mathematics, we would set up a system of equations with three variables, three numbers that I'm adding together, and we'd try to find three equations, and it might be difficult to do, but maybe we could figure it out sooner or later. Maybe we could do some back substitution or something like that. So what I'm going to do is we're going to work this, but we're going to try to keep it the way that Fermat would have done, or I'm sorry, Diophants would have done it, which is he's not going to want three different variables running around here if he can handle it, if he can make it not work. So I'll give you a little diagram. I don't know if he used a diagram, but we're going to use a diagram. And we're going to say we've got three numbers that are added together. And on one side, if I add, for instance, these two, I'll get a 43. If I add these two, I'll get a 51. And if I add these two, I'll get a 34. Now, the interesting thing with Diaphantus is it doesn't matter which ones I pick where, because we know that addition is commutative, right? So order doesn't matter. So if I pick these two, I get 43. That's fine. The combination of all the different ones will give me all the different sums. That's the point. Any two added together, I get these different sums. Okay, so what we're going to do is we're going to use this in one variable and one variable only. So we're going to let the total sum of all three numbers be our unknown. That's our plan. Okay, so we're going to call it x because that's my favorite variable, of course. Okay, so before we go any further, let me just kind of mark this down. So what we're saying here is if this is the first number and this is the second number and this is the third number, and we don't know what those are, when I add them together, I'll get x. So x is the first number plus the second number plus the third number. If everybody can agree with that, x being the total sum of the three numbers, that's how I would write it down. Okay, so what we're going to do is we shall make small little expressions for each of these numbers, first number, second number, third number, and that small little expression is just going to deal with the letter x. So I've got a first number, and I've got a second number, and I've got a third number. So for instance, we don't know what x is, but say that x is 71 because that'll make my life easy. Okay. If we know that these two numbers over here add together to give me 51, because that was given, and if I were to know that the sum was 71, the total sum was 71, then what would this extra number over here, number 2, be? In my mind, I hear you saying, well, of course, it's the total of 71 minus the sum of these two, which was 51. So number 2 would be, over there on that corner, would be 20. 71 minus 51. Okay. So if that's what we're thinking in our heads, but we don't know what x is, we don't know what the total is, then hopefully you can think, okay, well then how about we do x minus 51? That'll be one of my numbers. For my example, I should have put it on number 2, but you get the point. Okay, so whatever these sums are over here, those are sums of 2 of them. So if I subtract those 2 away from the total, I'll get the extra number, if that makes sense. So I need to subtract, subtract, subtract. So these little expressions here are x minus 51, x minus 43, and x minus 34. And again, it does not matter which of those you put that on. You could have made your first one x minus 34, and the second one x minus 51, and the last one x minus 43. It doesn't matter because we're adding, right? First number plus second number plus third number. So it's all commutative, order doesn't matter, and we can do it any way we want to. All right. So if that's the case, then now I should be able to just take these little expressions and substitute them in up above, right? First number, second number, third number. So now I have a really big equation. X equals, the total sum equals first number plus second number plus third number. So I'm just going to plug in x minus 51, x minus 43, x minus 34. So we just plug in for each of those, and now we have this lovely equation. I'm going to move up. We have this lovely equation that we can solve, and probably solve it pretty quickly. So x equals, this is 3x, minus, oh man, do I know what that sum is? 128. Check it and make sure. To solve this, I need to get all my variables on one side, so I'm going to subtract 3x. Negative 2x equals negative 128. So now I just need to divide by negative 2, so x is 64. Okay. And whenever I get here, I just take a small moment to check myself, because I know I'm working with Diaphantus, and I know all of his solutions need to be integers, and I know all of his solutions need to be positive. So, for instance, if somehow I had added this over instead of subtracting and I had positive 4x, and then I divided by positive 4, I would have a negative answer. If you have that, then you know that you've messed up somewhere. So no negative numbers here. Okay, so x is 64. Am I done? No, you're not done. That's what I hear in my head. No, this is the total of all three, right? Okay, so since that's the total of all three, I don't have my thing. It said find three numbers. Here's my first, here's my second, here's my third. So I need to do just a little bit of arithmetic. So for the first one, I'm going to do 64 minus 51. That's 13. I'm going to do 64 minus 43. That's 21. And I'm going to do 64 minus 34. That's 30. So check my arithmetic really quickly. 13, 21, and 30. So I think we're good there. So what I would say at this point, because I'm actually over time now, dang it, is 22 minutes now. So that's running out of the entire class time for today. What I would say is I want you to think about and solve the next one all on your own. So take a minute. It is actually from the book, the Arithmetica. This is actually one of his Diophantine problems. And what it said was find four numbers, and again I'm paraphrasing, such that any three add up to 20, 22, 24, and 27. Okay, so since it's four numbers, I'm just going to give you a little shove. Since it's four numbers, of course, we're not doing a triangle anymore. If we're doing the diagram, we would do kind of a square or a quadrilateral, and we would add three sides together, 1, 2, 3, to get our number, 20 or 22 or whatever it is. So if you use the same process, x would be the sum of all four. And you need to set up a little equation or expression here for all four of your numbers. The first number, the second number, the third number, and the fourth number. So you can go ahead and work on that and see what you get. Set up the overall equation, excuse me, and solve. And I will cheat by telling you, I'll give you the answer so you can check yourself. X should be 31, and your four numbers should be 11, 9, 7, and 4. That's my solution. So if for some reason you don't get that answer, rework it, work with a buddy, talk to somebody, put something on the student lounge, and or email me to see if I can help you with the solution. All right, that's it for this week. Thanks. Or for Monday's class.